Welcome to our quantum deep dive.
Oh, woo.
Today, we're really embarking on a pretty mind-bending journey. We're plunging deep into the extraordinary mind of Carlo Rovelli.
Rovelli. Yeah, one of the most brilliant theoretical physicists around today.
Exactly. And our guide for this, it's an incredibly insightful essay by Yorgo Schneepat, which really helps illuminate Rovelli's, well, profound contributions.
Right. And our mission for you today, really, is to try and unravel how Rovelli's groundbreaking ideas are fundamentally reshaping our understanding of the universe itself. He's one of those rare thinkers who manages to bridge, the often quite separate worlds of really rigorous physics and deep philosophy. And
Yeah.
maybe the most exciting part, his work is actually laying some vital groundwork for the future of quantum technology.
So why should you, our listener, care about all this deep theoretical physics stuff? I mean, sounds pretty abstract, right?
Well, yeah, it can seem that way.
Yeah. But Rovelli's work, it goes way beyond just equations. It directly challenges our most fundamental ideas about reality,
Yeah,
space, and especially time.
definitely time.
And it even provides the theoretical scaffolding for these quantum technologies that everyone's talking about, the ones that are really set to define our future. Okay, let's truly unpack this.
Let's do it.
So, to even begin to grasp the scale of Rovelli's vision, we probably need to understand where he came from intellectually. What was it that sparked his curiosity early on? What set him on this, well, pretty extraordinary path?
Okay, so Carlo Rovelli was born in Verona, Italy, back in 1956. Verona, famous for Romeo and Juliet,
Right.
opera.
Steeped in culture.
Exactly. And maybe that kind of early environment nurtured his later really unique ability to weave science together with philosophical questions, cultural ideas, making complex stuff resonate way beyond just the physics lab.
Interesting thought.
He started his physics studies at the University of Bologna, which, fun fact, is one of the oldest universities in the world. Really strong tradition in science there.
Wow.
Then his doctorate took him to the University of Padua, and that's where he really started focusing in on the big fundamental questions of gravitation. You could see he was already laying the groundwork for something major.
So even back then,
Yeah, right from the start, he was captivated by that huge challenge. How do you unite Einstein's general relativity, our theory of the very large, gravity, the cosmos,
with quantum mechanics.
precisely, with Werner Heisenberg's quantum mechanics, which describes the incredibly tiny world of atoms and particles? These two pillars of 20th century physics just seemed completely incompatible.
But Rovelli wanted to build a bridge.
He was determined to find a bridge. That was the quest.
That's fascinating. So it's clear right from the get-go, Rovelli wasn't just about the complex math, as vital as that is in physics. He was digging deeper, wasn't he?
Oh, absolutely.
Grappling with the big philosophical questions: what is reality? What is time? This mix, this blend of hard physics and deep philosophy, that really seems to be his signature, doesn't it?
It really is. That's what makes his work so compelling, I think. He saw the philosophical question as totally inseparable from the scientific ones.
It wasn't just about making the equations work.
No, it was about understanding what those equations mean for us, for our existence.
Okay, so we've got this foundational curiosity established. That brings us to one of his most massive contributions: loop quantum gravity, LQG.
LQG.
Now, this sounds incredibly complex. Can you sort of break down the core idea for us? Why is it so important in this big quest to understand the universe?
Right. Well, at its heart, LQG proposes something really revolutionary. It says that space and time, they aren't smooth and continuous like we experience them.
Not like a smooth sheet.
Exactly. Instead, they're discrete, granular. Think of it like the universe isn't a continuous canvas, but more like a finely woven fabric, or maybe even a digital picture made of incredibly tiny pixels.
Pixels of reality.
Kind of. The theory describes the universe as this network of quantized loops, like fundamental threads, quanta of space-time itself forming the very fabric of existence way down at the Planck scale.
Okay, the Planck scale. Help
Yeah.
us picture that. How tiny are we actually talking?
We are talking unbelievably small. Dimensions that just defy any kind of human intuition. The Planck length is roughly 10 to the minus 35 meters.
Wow, so a decimal point, then 34 zeros, then a 1.
That's the one. It's like the smallest possible pixel or thread of reality.
Yeah.
And LQG says these tiny loops form structures we call spin networks.
Spin networks.
Yeah, imagine the universe is woven from this incredibly complex, dynamic, always changing fabric at that fundamental level. And guiding all this mathematically is an equation called the Wheeler-DeWitt equation,
Okay.
which basically describes space-time not as some fixed background stage, but as a quantum system itself, shifting, interacting, just like particles do in quantum mechanics.
That is genuinely mind-bending. Now, when people talk about unifying gravity and quantum mechanics, a lot of listeners probably think of string theory first.
True, that gets a lot of press.
How does Rovelli's LQG carve out its own very different path compared to string theory?
Yeah, that's a really crucial difference, and it highlights a major fork in the road in theoretical physics. LQG works directly with space-time. It treats space-time itself as the thing being quantized right from the start.
Okay.
And its main focus is just quantizing gravity, creating a quantum theory of gravity.
Whereas string theory?
String theory comes at it differently. It suggests the fundamental building blocks aren't points, but tiny, vibrating, one-dimensional strings. And it's more ambitious in a way. It aims for a theory of everything.
A theory of everything.
Yeah, a unified description of all the forces, gravity, electromagnetism, the nuclear forces. So LQG is laser-focused on the quantum nature of space-time fabric, while string theory tries to explain all particles and forces as different vibrations of these strings.
So it's almost like LQG is trying to figure out the weave of the cosmic tapestry, and string theory is looking for the ultimate threads themselves.
That's actually a really good analogy, yeah. And the huge significance of LQG is that it tries to get rid of those infinities, those singularities we find in general relativity.
You mean like inside black holes?
Right.
Or the Big Bang?
Exactly. Those points where density and curvature supposedly become infinite and our current physics just breaks down. By quantizing space-time, making it granular, LQG stops those physical quantities from blowing up to infinity. It offers a way out.
A solution to those cosmic dead ends.
Potentially, yes. And here's another really wild implication. It suggests time itself might be quantized.
Whoa. So time isn't a smooth flow.
At the most fundamental level, maybe not. It might actually emerge as something we recognize, like a river flowing from all the interactions and changes happening within that quantum fabric of space-time, a bit like how temperature emerges from the jiggling of atoms.
Okay, this is where it gets really interesting for you, the listener, right? Because this completely messes with our intuition.
It absolutely does.
It radically changes how you might think about the very fabric of existence. It challenges that deep feeling we have that space and time are smooth, continuous backgrounds. Reality at its core could be chunky, not smooth, and time, maybe more like a series of ticks than an endless river.
Wow. It's a profound shift in perspective.
So, okay, the universe might be this granular quantum tapestry. Rovelli's mind then zooms in on an even more fundamental question, perhaps. What does reality even mean when you observe it?
Right.
Which brings us to his other huge idea, relational quantum mechanics.
RQM.
RQM, yes. Another paradigm shift.
This seems to take the idea of observation somewhere totally new.
It really does. RQM basically says that physical objects don't have inherent absolute properties just sitting there on their own.
They don't exist independently.
Exactly. They are defined only in relation to other objects, through interactions. So, crucially, this means there isn't one single objective reality that exists independently of any observer or any interaction.
Yeah, no objective reality? According to RQM, no. Every measurement, every interaction is simply a relationship between two systems. A system's state, what it is always relative to some other system.
It's defined by the connection.
By the relationship, the interaction, the connection, not by some absolute property it possesses in isolation. What something is only makes sense relative to something else.
Okay, if I'm getting this right, it's not just that observing affects reality, which is kind of the standard quantum takeaway, right? It's that reality is the relationship, the interaction itself. That feels like a huge leap.
It is an enormous leap.
What are the implications of that? Philosophically, physically?
Well, philosophically, it completely challenges that idea of an objective universal reality just out there, independent of us or any interaction.
Right.
Instead, RQM pictures reality as this dynamic network of relationships, constantly shifting, interacting. This hits hard on ontology, what exists, and epistemology, how we know things.
If there's no objective thing, then all knowledge is contextual.
Precisely. And physically, it offers new ways to think about some of quantum mechanics' old nagging problems, like the measurement problem.
Ah, the mystery of why quantum states collapse when measured.
Exactly. RQM suggests the collapse isn't some absolute event happening everywhere. It's just the establishment of a new relationship, a new correlation between the system being measured and the measuring system.
So the wave function isn't describing an absolute state.
It's describing the information one system has about another within that relationship.
Okay, this raises a really interesting question then. If reality is fundamentally relational, defined by interactions, how might your observation, your unique viewpoint, actually shape the world around you? It makes you think differently about your own role, doesn't it? Your connections. It shifts the focus from what's out there to what's out there in relation to me.
Exactly. It puts the interacting system, the observer in a broad sense, right at the heart of defining reality, not just passively receiving it.
Okay, shifting gears slightly. Beyond this incredible theoretical work, Rovelli isn't just locked away in an ivory tower, he's also known as a master communicator.
Oh, absolutely. One of the best.
It's one thing to devise these incredibly complex ideas, but it's totally another thing to make them accessible, engaging for us, the general public. How does he do it?
I think his approach is really special. He deliberately avoids that dense technical jargon that just puts people off, you know?
Yeah, the equations can be intimidating.
Totally. Instead, he uses these vivid, almost poetic analogies and metaphors. They help build an intuitive feel for the ideas. And he brilliantly weaves in philosophical reflections, historical context, even little personal stories.
So it's not just dry physics.
Not at all. It illuminates the complex topics, connects the physics to the human experience. His books always highlight the beauty, the wonder, the really deep questions that physics tackles. They feel less like textbooks, more like conversations.
Like he's exploring with you.
Exactly. He shows that physics isn't just formulas. It's about finding our place in the cosmos.
And he's had huge success with popular science books. Which ones really stand out as examples of this gift?
Well, the obvious one is 7 Brief Lessons on Physics. It was just a global phenomenon.
Right. Tiny book, huge impact.
Incredible achievement. Translated everywhere because it gives you this incredibly concise yet really profound tour of modern physics, relativity, quantum mechanics, cosmology.
All in just a few pages.
And always with that historical context, those philosophical insights. It feels both educational and deeply human. Then there's The Order of Time.
Ah, yes, another mind bender.
Totally. In that one, he takes on our basic intuitive idea of time as this linear flow. He explains how, at the fundamental level, time as we know it might not even exist.
Like we discussed with LQG.
Exactly.
Okay.
It might emerge from deeper, more fundamental interactions, maybe linked to thermodynamics. It completely shifts your perception of what time is.
Which is just, wow. And this accessibility, making these ideas understandable, that's so crucial, isn't it? What does his popularization mean for, say, the next generation? For you as a learner, maybe an aspiring scientist, or just anyone curious?
It has a huge impact. His writing doesn't just explain things, it really ignites curiosity.
It makes you want to know more.
Exactly. It encourages young physicists, for example, to think beyond just the math, to explore the deeper meaning, the philosophy behind it all. And for philosophers, his ideas, especially RQM, are sparking really lively debates in metaphysics and epistemology.
Challenging old assumptions.
Definitely. And what's also great is his interdisciplinary approach. He connects science so effortlessly with literature, with art, poetry even. It really shows how physics is deeply rooted in human culture and our creativity.
He makes science feel like part of the bigger human story.
He really does. He sort of democratizes the wonder.
Okay, so we have these abstract theories, these eloquent books. But how do these complex ideas from Rovelli actually connect to the real world? Especially in this exploding field of quantum technology. It seems like such a big jump.
It might seem like a leap, yeah, but the connection is actually surprisingly direct in some ways. Rovelli's deep understanding of, say, quantized space-time structures from LQG that provides a fundamental theoretical underpinning for accurately simulating complex quantum systems.
Which is crucial for things like quantum computers.
Absolutely. Quantum computing, quantum communication.
Yeah.
And his ideas about relational states from RQM, those precise mathematical descriptions can directly feed into developing more efficient quantum algorithms or even optimizing how quantum computers are built.
How so?
Well, if reality is fundamentally relational, then building a computer that leverages and understands those relationships, how information is defined between systems, becomes key.
Can you give some maybe more concrete examples? Where might these ideas actually be applied?
Sure, in quantum computing, insights from RQM could help develop more robust quantum protocols. Quantum computers are incredibly sensitive. They need to maintain this delicate coherence.
Right. Errors are a huge problem.
Exactly. RQM's relational view helps us understand how quantum states interact and maybe maintain stability better within these complex systems. That could make fault-tolerant quantum computers more feasible.
Okay, that would be huge.
And in quantum communication, relational approaches could improve quantum encryption. If you understand the dynamics of interacting systems better, especially how information is encoded and transmitted relationally, you might enhance the security and efficiency of sending data over quantum networks.
So he's not just theorizing in isolation.
No, not at all. He's actively involved in promoting this kind of cross-disciplinary work, bridging the gap between the really abstract theory and the experimental application.
That's incredibly powerful. So what's Rovelli's bigger picture view, his vision for the future of quantum tech? And does he raise any ethical flags for us as things develop?
He definitely sees quantum technology as a key development for this century. He genuinely thinks it has the power to push past the limits of classical physics, maybe even help us answer really deep questions about the universe's origins through advanced quantum simulation.
Like simulating the Big Bang.
Potentially, yeah. Imagine that level of detail. But he's also very grounded about the societal impact. He stresses the ethical responsibilities that come with this power.
It's not all just progress.
No, he talks openly about potential challenges, like the impact on cryptography, data privacy, the dual-use problem inherent in powerful tech. He's not some tech utopian. He really advocates for science to be integrated into the bigger goal of creating a more just, sustainable world.
So the tech should serve humanity.
That's his argument, not just progress for progress's sake.
Okay, it's clear Rovelli's work is brilliant, it's innovative, deeply influential. But like all cutting-edge physics, it's not without debates, challenges. We should probably touch on that too.
Oh, definitely. That's part of the scientific process. His strengths are undeniable, though. His unique approach, blending that mathematical rigor with really deep philosophical insight.
Yeah.
His leadership in developing LQG, building a whole community around it. And RQM is such a challenging, fresh reinterpretation of quantum mechanics. The awards, the citations, his role as a mentor. It all speaks volumes.
But the challenges?
Well, the big one for LQG is experimental verification. Right now, we just don't have the technology to directly probe the Planck scale.
We can't see the pixels yet.
Pretty much. That's a hurdle for any quantum gravity theory, to be fair. And RQM, its radical interpretation of reality is still hotly debated. How does it stack up against string theory or other interpretations of quantum mechanics?
So the jury's still out on some things.
Absolutely. And that vigorous debate is healthy. It pushes the boundaries.
So when we take a step back, look at the whole picture. What's the bottom line for Rovelli's long-term legacy? And maybe more importantly, for your future understanding of science, of the universe. What's the lasting takeaway here?
I think despite the ongoing debates, which are totally normal at the frontiers of science, Rovelli's work has undeniably opened up completely new paths in theoretical physics. He's really pushed our understanding of space, time, quantum mechanics.
He's given us new ways to think.
Exactly. Fresh perspectives. And his ideas, especially about relational states, they genuinely hold significant potential for future tech, like quantum computing, things that depend on understanding quantum interactions deeply.
And beyond the science.
Beyond the purely scientific, his influence is much broader. That interdisciplinary connection he makes, physics, philosophy, society, ensures his legacy will go far beyond academia. He's essentially invited everyone into the conversation about the universe's deepest mysteries.
He really has. So, to wrap up our deep dive, Carlo Rovelli is just an extraordinary figure.
Truly.
He's that rare person who not only pushes the absolute boundaries of theoretical physics, but also inspires millions with his clear explanations, his thoughtful blending of science, philosophy, culture.
It makes you want to be curious.
Totally. He encourages us all to question, to wonder, to marvel at the universe.
Yeah, he definitely stands alongside the greats, like Einstein, Heisenberg, not just for his physics contributions, but for how he's kind of redefined our understanding of the world itself in his own way.
His work reminds us science is as much about the questions as the answers.
Absolutely. The profound questions.
And for you, the listener, here's maybe a final thought to chew on. If reality truly is fundamentally relational, if it's all about interactions and connections, not fixed things, how might that perspective change how you view your own observations, your own connections in your daily life?
That's a deep one.
Something to explore, maybe.
Definitely.
Thank you so much for joining us on this quantum deep dive. For more fascinating insights into Carlo Rovelli's work and other cutting-edge science based on Schneppat's research, you can explore the works of Yorgo Schneppat over at schneppet.de.
Great resource.
We really look forward to diving deep with you again soon.